Hello, everyone. Good afternoon, everyone. We will be shortly starting our webinar. Thanks for joining. We will just wait a couple of more minutes to let everyone join the session. For now, thank you all for tuning in for this webinar on fluid and powder simulations via Particleworks and Granuleworks. We will, in a couple of seconds, start with this webinar. And in the meantime, just feel free during the talk to ask question. I will provide answer at the end of it. I see people are still joining, so we will wait 30 more seconds and then maybe we can start by giving an overview of the agenda of today. Thank you all for joining again. I see people are still coming. Okay, so by the way, I hope that everything is visible and you can hear me correctly. So I will slowly start as people are still coming, but let's first have a look at the agenda of today's webinar. So the main topic will be Granuleworks, that is a powder or let's say granulate material simulation tool. I will discuss this meshless approach for powder simulation, and actually, after discussing the numerical models implemented in Granuleworks, we will see how it couples with other software, and actually the main software it's coupled with is Particleworks, that is for fluid. Okay, so the idea is that here we are discussing the same software but with two tools, one for granule material and the other one for fluid. And I will explain in detail how the two software can couple and what type of physics can be coupled. And then we also discuss RecurDyn coupling. This is another software, yet another software for multi-body. And then we will have a look at the industrial applications where Particleworks and Granuleworks are applied. Here we have some videos showing some of the feature with airflow moving what was the Granuleworks text, and then some mixing or like also thermal analysis. I hope the agenda is clear. We can, I think, start by giving a quick introduction on the tool. Granuleworks is a meshless tool for powder simulation. So it means at the beginning of the simulation, each granular element is discretized automatically by the software, and we don't have to have a computational mesh to be generated in advance. Okay, so the software handles the meshing and also the dynamic uh, computation on that mesh. What we solved here on the solid or powder side is discrete element method equations. So basically, we will see in the next slide Newton's law and contact forces, but also other type of interaction that usually are found in powders. In terms of application, of course, here we are looking at processing, mixing, dosing of powders, but not only that, powders mixed with fluids, for instance. And because of that, we have application in healthcare, civil engineering with concrete flow, healthcare for tableting or coating of tablets, as well as mixing of again, powders and non-Newtonian, very viscous materials, and so on. So we have a wide range of applications in different industrial sectors. As mentioned, basically, Granuleworks is a very simple approach because it doesn't have to mesh the fluid or the solid domain, and also every complex geometry can be integrated, or very complex also motion, or like, let's say, shaking effect and so on, can be integrated easily. We solve for rotation and translation of the powders, and applied also the interaction and collision and exclusion of volume, of course. We have friction, slip, and other type of, let's say, interaction between the particles. So we have conveying systems analyzed, for instance, and so on. But not only that, we have integrated models to have a more refined interaction and modeling of the flow, meaning that we can, for instance, have liquid bridges, so liquid-like adhesion forces on the powders, and also rolling resistance, so we can also account for the losses of energy due to rolling of the particles. Van der Waals forces can also be integrated, so basically for very small particles we start to have electrostatic attraction, and also that results in more adhesion. So as you can see, when the van der Waals force model is integrated, particles, especially small particles, act in a different way. And we have also a thermal solver to see how the temperature of the powder is also influenced by the boundary condition of the system. And we could also have temperature dependent viscosity if we have the fluid combined with the powder, viscosity variations. Another feature of the software is that we can have a user-defined granulometry. So basically, we can deal with a distribution of sizes in the particles. Those can be user-defined or also log normal, or let's say some other standard particle size distribution. So as you can see here, we have a shaker and a multi-step filter for powders, and based on the dimensionality, some particles can flow through while others get stuck. Also, a new feature of the software of the latest release is to have custom shapes, not only like spherical particles, but also, as you can see, rectangular and capsule like particles. So that is also very interesting because, of course, the geometrical feature of the particles can influence the flow, like in this case, depending on the type of shaking and the, let's say, shape of the powder, we can have higher or lower mixing or flow. Here is another example of that implementation. So we have a conveyor and a vibrational feeder, that basically the objective is to have a selection of, in this case, bolts. So it's a very custom shape, also anisotropical. And as you can see, the system selects and drag the bolts around the screw around, and they are then transferred to this container. A similar, let's say, approach on the right, where we have a linear drum feeder in this case, but the objective is basically the same. So we have a very wide range of motions, very complex, let's say, dynamics that we can easily implement it because of the meshless approach of the software, and then, let's say, analyze the system and understand if there are bottlenecks or blocks or have a quantitative insight on the type of flow that we reach. So the idea is to also have geometrical features or like testing digitally several conditions before maybe producing prototypes, of course. Finally, still discussing the multi-shape property, we can see here that we have three different filters, or actually the same filter but acting on three different powders. And based on that, we can have higher or lower flow, of course. And by the way, here you start to see the coupling because in light blue we have a fluid, so modeled with in this case, Particleworks, so the other software that we will discuss briefly. So the flow of the powder is dragged by the fluid flow in this case. And there is a reciprocal interaction with also bubbles forming possibly. One of the most typical parameter in granular flow is the angle of repose. This can also be integrated in a Granuleworks analysis. So basically, the angle of repose is the angle that a certain test, like the one shown here, will result given a certain powder. Of course, powders can differ greatly because of the whole interaction that we discussed. So one of the first thing that we do usually is to have this kind of simple test that is also usually replicated experimentally to have a fine tuning of the material properties of the powders. And then, given this angle of repose, we can control indeed the correlation between the physical testing and the modeling we are doing. The angle of repose is influenced by, of course, the shape of the particle themselves because of the different interaction and exclusion we have. So we can clearly see here the height of this cylinder at the end of the let's say simulation that differs based on the geometry. Another cool feature is the scalable discrete element method. So it's a numerical method integrated in the software that lets you basically simplify a bit and speed up the simulation. You can see here that starting from a particle size of 2 millimeter, we can go to 6 millimeters, so with a coarse grain model of 3. So the idea is that we can have similar behavior, but with significantly lower number of powder particles and faster simulation times. So in this case, we can do some numerical correlation and have a faster simulation once we know the system, basically. And by the way, also here it's interesting because we see another coupling. What you see in the background is actually air flow solver based on a finite volume method that is integrated in the software and coupled with the powders easily. Okay, so here we see air coming from the side that, let's say, drags the particles in a dynamic way. And the SDM method, as you can see, lets you achieve very similar results, but with significantly faster simulation. So it's a good way sometime when we can have a little bit of flexibility on the accuracy we want to have to speed up and maybe to have, let's say, 1 hour total simulation or even minute simulation. Okay, let's now move to the couplings. I already mentioned that there are several couplings. We already saw some of them. The most important couplings I would like to mention is with Particleworks. So Particleworks is the fluid solver that shares actually the interface of the software. So basically, you open up Particleworks and you see also Granuleworks inside as a separate model for granular materials. And here we have a couple of industrial systems in which we have the two phases modeled together. Fluid is in light green here in a separator, and powders are, let's say, in brown. So you can see that granular material is coupled with the very viscous fluid. Actually, in this case, it's water, so normal viscous fluid. But on the right, we have a mixer with powders dispersed in a very viscous, in this case, let's say, matrix that could be a slurry or similar. And you can see that we can evaluate easily geometrical feature of the impeller and see how the powders are dispersed during the mixing. Because again, it's a meshless approach, this kind of complex geometry is no issue. And also, if we want to test, let's say, more RPM condition or whatever, we can easily do that. Here we have another coupling. I see there are some questions. I will address those at the end. Thanks for asking, though, already. Here we do see another example of the coupling. In this case, we have basically a powder material and then a very viscous additive that needs to be dispersed in the powder matrix. You can see on the right only in color the viscous material. And what's interesting here is that we also have actually the temperature evolution because this system has some thermal boundary condition on the walls. So we do see some heating of the powders. And we can also understand how the heating is distributed around. You can see here that there are some accumulation of fluid and also powders. Discussing an industrial example of this type of solver, fluid and powders, I think it's worth mentioning Lorenzo Iorio presentation from Gamma Meccanica. We had Lorenzo at our conference in 2023, and he discussed plastic recycling machines. So basically, in this kind of system, we have an injection of powders, that is a plastic pellet, and water on the right side. Water needs to be discharged at the bottom, while the pellet needs to be separated by the rotor. So the idea was to model this system, optimize the rotor to achieve the highest throughput at the top while keeping the water intake and, let's say, volumes as low as possible. In that way, we reduce also the losses, of course, of the rotor because we have less water around. You can see here another objective was to confirm preferential paths on the rotor of the particles to understand where the most erosion could happen. And you can see here that on the right we have indeed this kind of flow that is confirmed by Particleworks mapping post-processing. And the output, as mentioned, is rotor power losses. And you can see that different rotors will result in different losses. So one iteration was on the rotor design. So in 1 week, Lorenzo could test more than 3 design and identify the optimal geometry for lower losses, but also bigger granulate flow. So the idea is really to push a simulation earlier in the design because of the meshless approach, because also of GPU acceleration, so graphic cards acceleration, to achieve faster engineering, design, and insights. Here is another type of system we can easily address with the coupling. So basically we have a feeder in a separator with a fluid and a solid that needs to be discharged separately. So solid phase is usually separated in this kind of system at the front, and the sludge will separate again because of the rotation of the feeder and also the geometrical feature applied, and also the physics because of like different interaction and densities and so on. So you can see here in the example, this is the animation. On the left, we have the injection of the two materials that are separated by the fluid and the solid. Another feature that we can easily integrate is the finite volume method. I mentioned that it's not only fluid, what Particleworks can integrate with Granuleworks, but also air simulation. So basically here we have the granular and an air field computed with the finite volume method. The finite volume method is an integrated air solver based on a Cartesian grid automatically computed by the software during the simulation. Okay, so again, it's a meshless approach, and the advantages of having air model separately with a different solver is that we can have a bigger cell size for air rather than the solid part. Okay, so you can see here uh, a wheel simulation, the airfield due to the wheel, and the interaction between the solid but also the airfield. The coupling with the air solver comes handy also for respiration system or transport of powder by air and pneumatic transport. You can see here on the left we have an aspiration system, and depending on the boundary condition or like the pressure applied, we can have better or worse type of aspiration. And then on the right we have this dynamic flow pattern that arise when we have an air inlet and then some accumulation. So very complex physics to be analyzed with mesh-based tools. But here, because of the meshless approach, we can easily, let's say, model it all and have this kind of dynamic interconnected flow. The airflow system and solver is also very important for a fluidized bed system. So you can see here at the bottom we have an air inlet, and then the fluidized bed particle that needs to be, let's say, moved and let's say recirculated. And you can see here in the background the air result and the flow of air due to the transport of the powder, and the other way around, of course. So in this way, you could compute the flow in different areas and understand again your system in a better way. Here you see the flow in the red area, and in green the flow at the outermost circle. And as you can see, it's higher in this area rather than in this one. Finally, another coupling we have is with RecurDyn. So RecurDyn in this case is an external solver that handles multi-body system. So basically, very complex kinematic rotation could be applied and handled by this multi-body platform. And also the software here, RecurDyn, has a library of also analytical contacts between the system, so we can really study friction and define forces on the elements to achieve movements of the multibody. Here, just to show you some example, we can have a flexible fluid. The video is not playing. Let's see if I can recover that. Sometime. Okay. But the idea is that this, let's say, spatula, this system is actually flexible, so you cannot see it now, but this element can bend significantly due to the interaction with the powder. On the right, we have von Mises stresses computed directly on the very complex, let's say, motion described by RecurDyn. So for this kind of other application, and you can see also that the solid and the motion of the excavator is influenced by the powder itself. So very complex coupling between multibody and powders. Other industrial application, we already saw some mixers. Of course, this is one of the main fields of application for Granuleworks. I will just now go through some videos just to give you a broader view of where Granuleworks is applied. Again, feeders and different kind of shakers systems. You can see here we have multiple feeding areas. We have shaking to have more or less shaking or control the distribution of particles. Here we do see the multidimensionality as input, and again, giving a certain kinematic law, we can understand how the system behaves. This video shows the flow and how a certain, let's say, geometrical feature can impact the final distribution. Also, chemical coating and dispersion of particles in a matrix can be analyzed. Here we see the correlation between an experiment and, let's say, the diffusion of this coating element. You can see that as we progress, more and more pink particles gets to the left side, and as confirmed by the simulation output. Compression of the powder is also a mode, let's say, a physical property we can integrate in the software, and this is very interesting for molding, for elastoplastic modeling of material. So you can see that the shape is changed significantly and kept constant because of the forces, attraction forces that results at the compression. In tableting of, let's say, drugs, this is very important. You can see here that at the beginning there is this kind of powder distribution, and then we have the formation of the tablet and the transport of it. As mentioned, let's say machinery or like construction materials is also a field of application. In this case, we have concrete. As you know, concrete can be modeled by powder, let's say powder dispersion or filler inside the cementous matrix. That is a very viscous fluid-like material. So you can see in black the matrix, like the carbon blacks that are dispersed in concrete. And in gray, you have the cementous matrix. And of course, depending on the percentage of solid filler, we can have different type of flow patterns and velocities. So you can see here that actually having more powders will slow down in some cases the flow. Here again, a couple more examples of industrial systems that are analyzed where powders, like in drilling or again mixing, are present. Civil engineering applications are of course also of interest. Here we have a natural dam system and the study of how this natural dam could impact the flow or let's say change the river flow accordingly. So if we have actually some sort of undesired event like an avalanche or some debris accumulating on the river side, we can see again how the fluid flow is impacted by it. And here we have several shapes, like more elongated system that could model trees and more, let's say, squared or cubic elements that could model rocks. Taking advantage of the multi-particle, multi-shape feature of the software. At the end, we see here snow modeling, and actually this one is an advanced model because we do also have, again, adhesion forces typical of snow and accumulation. And as you can see here, the accumulation is modeled by these forces. There are adhesions between particles, but also on the walls that will result in an accumulation that then falls down to gravity when, of course, the physics the obeying physics will result in that. We have also a tire entering a snow pattern, and we can see the tire tread compressing the snow accordingly. Still on the coupling and on the snow modeling, here we have an airfield, so let's say a very strong atmospheric event where snow is dragged around by the wind. And as you can see on the right, we have the airfield that is impacted by the accumulation of the snowflow. At the beginning, the snowfall will be only in this area, but then it accumulates and the airfield changes accordingly. So, of course, this kind of dynamic aerodynamics that results because of the fluid or the powder accumulation is of great interest in civil engineering applications. And here is the last example, still regarding snow and accumulation in a traffic light with uh, a wind coming from the side. You can see here that there are some areas where particles don't accumulate because they accumulate on the signs placed on the street. So to conclude, today we saw Granuleworks, the discrete element solver for powders and granular material integrated in Particleworks. We saw the multiphysics capabilities and the coupling we can have with air, fluids, and also rigid bodies, so the multi-body solver. And then we have a look at some of the application where Particleworks is most used, like mixer, fluidized bed, machinery, plastic recycling, concrete, civil engineering, and also aspiration system. So very wide range of application and couplings we can have. Of course, it really depends on your system and your features, but you can see that the flexibility both in the kinematic and the, let's say, modeling is very wide. So I'm pretty sure we can maybe address some of the application you could have in mind. And talking about that, feel free to activate and reaching out to us, activate a trial. We can have a specific call with you to understand your system and either give you access to a trial of the software and a training, a free training, or maybe build a custom proof of concept for you to understand if indeed you can get value from this digital modeling. Okay, so please again, feel free to reach out to the email here for any question that might arise or interest. Now I will take a look at the chat as there are questions. Alexander asked a couple of questions here. I think we do have also a Q&A. So Alexander asked, what is the upper limit with respect to number of particles for a feasible simulation setup? There is no upper limit. We can handle millions of particles. What is usually also a limiting factor could be total simulated time and the time step used for the simulation. So it's not only the number of particles that, of course, will impact the simulation, but the time step, so the iterative time step, and also how much we have to simulate, okay? But there is no strong upper limit. Continuous, the other question is about if we support continuous methods such as Euler-Euler method. This one I'm not sure what you mean specifically. If it's So we are doing a Lagrangian modeling, so the meshless simulation is a Lagrangian type of approach. So the Eulerian approach is on the only on the air, so the finite volume method solver. Which technology is used to model the fluid behavior is, as mentioned, moving particle simulation, so MPS, that is a Lagrangian approach, similar to SPH. The difference between SPH and MPS is that MPS is for incompressible fluids. That is usually the case for this kind of system. And because of that, it's usually faster than SPH because the stability condition is less demanding. We have contact model for concrete available. Yes, we have several on the fluid side, so the non-Newtonian part. On the fluid side, we have several viscosity law that can be table defined, user defined, or predefined, like Herschel-Buckley or power laws. So wide range of shear, but also temperature dependent viscosity law. Gennaro asks what input parameter are required to characterize the powder motion. Again, usually is the contact forces, the electrostatic forces, but what we can do usually is to have first an experimental setup, a simple setup, again as shown, the angle of repose, to match numerically the behavior, and then once we tune these numerical parameters, we know that the flow of the powder is represented. So even if we don't have, let's say, all the powders, because usually it's very difficult also to extract the measurement, even if we don't have all the powders properties and measures, we can do correlation, okay? And then regarding beans, again, yeah, I think it's very possible to do that, and it could be of interest. What type of characterization is required to ensure reliable simulation with less than 5% deviation from experimental results? Of course, especially at the beginning of of the use of the software, some tuning or some correlation could be necessary, and it's difficult to say uh, one shot or like before looking at the system, especially for novel system, what type of correlation gaps we could have. We have several validation of different aspects of the software already done, but it really depends on the type of system and the physics we want to apply, okay? So, but what's interesting is that because of the fast simulation times, we can do this kind of iterative also on the numerics, initial iteration or check, much faster than other CFD tools, okay? How long does it take to run the couple simulation of fluidized bed? Again, it really depends on the volumes involved and the feature size we want to resolve, but that can take some hours or like 1 or 2 days. But what's interesting is that uh, a lot of that is computational time. So the simulation preparation, that is man hour, is usually in the range of 1 hour. Okay. And then once you have the setup, you just need compute. And the compute is faster every day because of technological trends like AI or other, as we use basically the parallelization technique that are also used in artificial intelligence models running on GPUs. Okay. I hope this answer your question. Please feel free to continue asking if you want some additional clarification. And many thanks for now for all of the inputs, very important, of course. I hope uh, I hope everything was clear on the feature and the modeling. I will wait for a couple more questions, maybe. You can find in the chat or the QA. If on the other end we don't have other curiosities, again, I invite you to really get in touch with us and maybe schedule a personalized call to perhaps go in detail on your system and understand if indeed it can be modeled and what type of simulation time we could look at. And again, the software is very easy to use, so also a trial of it is usually very beneficial to understand where it could lead your R&D development. Okay, see another chat question. The coupling solid and fluid solver is fully integrated and running on GPU. Yes, solid is Granuleworks, it runs on GPU. Fluid Particleworks is running on GPU. So everything is in one interface, sharing the pre-process and post-processing. So you don't have to learn two software or open two software. Yes, and everything runs smoothly. We can run only fluid, only solids, or both, by the way. Okay, if that answer all your question, thank you again for tuning in. It was a pleasure to have you all. And again, I hope to talk with you soon in the coming days and weeks. Thanks again, and have a nice continuation of day.